Hello, how's it going? It's Mr. Munoz. Here's the quick explanation of how to simplify radicals with variables. So when we simplify the variable portion of a radical, we just kind of got to do this. Understand that the square root of a variable term is half of the even numbered exponent. So as we look at some of these, if the exponent's an even number, such as this, like x squared, we can just take half of it. The square root is x. Same thing for this one. If it's k to the 10th, since 10 is an even number, I can just take the square root by cutting the exponent in half. Half of 10 is 5, so the square root of k to the 10th is k to the 5th. However, when the exponent is not an even number, what we have to do is divide it or break it down to the next lowest even number, and then another variable to the first power. So it's end of the 5th, you break it down to be end of the 4th, the next lowest even number, times n. So it still is equivalent to end of the 5th, but it allows us to take the square root of the end of the 4th, which is n squared, and then that variable that's just end of the first power, you can't take the square root, so it stays in the radicals. So square root of n to the 5th is n squared radical n. Same thing with this one, square root c to the 19th, we make it c to the, we make it c to the 18th times c, so it's still equal to c to the 19th, except we're able to take the root of c to the 18th, it's c to the 9th, square root of c, and you kind of see the same thing here. If it's even numbered, you just cut it in half. 6 is even, so I can just cut it in half, and the square root of y to the 6th is y to the 3rd. The odd numbers, such as x to the 13th, we make it into the x to the 12th times x, and we can take the square root of the even numbered exponent, x to the 12th, and the square root is half, so it's x to the 6th, and dang it, I messed this up. That should have stayed an x, not a 6, so that should be an x. And then here, same thing, p to the 29th is an odd number, so we make it p to the 28th, the next lowest even number, times p. We can take the square root of p to the 28th, it's p to the 14th, and we're good there. So you kind of see that same thing happening, and then eventually you have variables and numbers, and so the 18, I break it down the same way we've been doing the last couple days, and it ends up being, I can pull out a 3 and a 2 stays in, and then the square root of the y to the 8th portion is y to the 4th, and that comes outside the radical. Same thing on these. It's the 27 we break down in that same manner that we've been breaking things down the last couple days. So 27 is 3 times 9, then 3 times 3, and we can take out a 3 because there's a pair of 3's, but then this 3 by itself has to go back inside the radical. So 1 3 comes out, 1 3 stays in. The y to the 13th, we make it into y to the 12th times y. And we take out the square root of the y to the 12th, which is y to the 6th, and this y has to stay in the radical. So definitely did the same thing on these. Eventually, I kind of want to use square roots to get my answers and not always make a factor tree, so you'll see that on the next page. So on this page, you see a lot of the same here. I break down, I did use a factor tree on all of these. This one didn't require a factor tree, guys. Remember, if you have a perfect square, try to just remember that you don't really need a factor tree. 4 is a perfect square. The x to the 3rd, though, I need to break down to x squared times x. And I can take the square root of 4 is 2. The square root of x squared is x. And this x doesn't have a square root because it's not an even numbered exponent. It stays in the radical. This right here is perfect squares. The square root, or 81 is a perfect square. Y to the 12th is even. So I can take the square root of 81, it's 9, and the square root of y to the 12th is y to the 6th. There's nothing left in the radical on that one. Then, as I get through these, I notice perfect squares on some of them, so I didn't break anything down. And then I started using the perfect squares that are hidden inside of these. So I didn't make a whole factor tree for these. For 12, I just used 3 times 4. 4 is a perfect square. 3 is not. The square root of 4 comes out as 2. The 3 has to stay in the radical, as you see here. And then we have x to the 15th. We need to break it down, as you saw on the first page, to x to the 14th times x. and the square root of x to the 14th comes out, it's half, it's x to the 7th. The square root of y to the 12th comes out, it's half of 12, it's y to the 6th, and this x by itself has to stay in. So throughout these problems, I did use perfect squares. Like 4 is already a perfect square. 50, I use 2 times 25. I take out the square root of 25. There it is, it's 5, and then the 2 has to stay in the radical. And the variables, I just do the same thing as what I was doing on the first page. If it's even, I just take half of it. If it's odd, like 21, I make it the next lower number with an extra y. Then I can take the square root of y to the 20th, which is y to the 10th, and this y has to stay in the radical. So the pattern, the steps just kind of continue here. 80 I know has a 16 in it, which is a perfect square, so I use 5 times 16. The square root of 16 comes out as a 4, the 5 stays in. The c squared, you take the square root of that, which is c. D to the 3rd you break down a little bit, as you see here. You take the square root of d squared, which is d, and this d has to stay in the radical because it doesn't have an even numbered exponent. Kind of see the same thing on these, so definitely use this video as needed. Thanks for having a look.